Howdy, students. This is going to be a brand new chapter that we're going to cover a little bit more of titration and buffer solutions. So today, the objectives in lesson 1 are to identify the common ions in equations, and then we're going to start to describe what happens when we do, in fact, add a common ion to an equilibrium system. We call it the common ion effect. And then we're going to move into what buffers are in 15.2 and examine buffered system equations. With these buffered equations, we can still set up Rice tables, and we can learn a new tool called the Henderson-Hasselbalch equation. Let's get started. The common ion effect is when we have a weak acid equilibrium system, and we are going to add an ion that is already present in the equilibrium system. So in the image on the left, a strong acid, if it were to supply H3O plus to the system, what we know is that we are going to shift equilibrium to the left according to Le Chatelier's principle. So the addition of an ion that's already present will shift away from the common ion. And that's a skill that we should have learned in previous units. So for instance, if I were to add the addition of acetate ion, what would actually happen in here is more along the lines of the common ion effect that we're talking about. And what would happen is we would shift equilibrium to the left. But what's really important if we made that addition is that the concentration of H3O plus or H plus would actually go down. And so we would actually be decreasing pH. So we're going to look at that in just a little bit. Another example here, if we were to add NaF, a basic salt, well, it would ionize completely into Na plus and F minus. Well, from our equilibrium system with hydrofluoric acid, we know that F minus was the common ion. So if we are making an addition of more F minus ions, then equilibrium is going to shift to the left, and thus fewer H plus ions will be present. And if we are decreasing the concentration of H plus in solution, we are going to be making the pH actually rise. So if we add a common ion to a solution of weak acid, it will make the solution less acidic. That would be increasing the pH, fewer hydrogens. So let's say that we add sodium acetate to an equilibrium system of acetic acid. Well, we know that the common ion here is the acetate ion. It will shift equilibrium to the left, thus decreasing the concentration of H plus and raising the pH. We can calculate a new pH by putting the concentration of the anion into the Ka equation, and we can actually solve for the new value of H plus. Now, I want to be super clear. Ka is never going to change unless temperature changes. So this will stay the same unless temp changes. And in most of these examples in this unit, we will not be changing temperature. If we do change temperature, we'll have to be given a new Ka value, or we will be solving for it. So let's go ahead and solve our first common ion problem. A solution contains 1.0 molar hydrofluoric acid and 1.5 molar Kf. What is the pH of the solution? The first thing that I notice is that we have HF, a weak acid, and we're mixing it with a basic salt, Kf. And what I want you to understand is that there is no reaction happening. There will not be a chemical reaction taking place. They are just going to be hanging out in solution together, mixing or dissolving where the ions are interacting. So our equation, our equilibrium system for hydrofluoric acid is here, HF. We can write a Rice table, and the only thing different here is that we now have the addition of a common ion, F minus. So initially we have 1.0 molar And just remember that Rice tables are for concentrations or partial pressures, which we saw in a previous unit. There is no initial H plus concentration, but what you'll notice and what I'm going to draw attention to, the big change here, is that we are adding 1.5 molar of that common ion because we're assuming that it dissociates completely. And this is 1.5 molar for concentration. We're going to see our normal minus x and plus x's because equilibrium is going to shift to the right. We are needing to create hydrogen. Equilibrium values are as follows: 1.0 minus x for hydrogen, x. And then for F minus, something that maybe looks a little different is 1.5 plus x. We're going to use the Ka value for hydrofluoric acid. So this is the Ka because we're writing a weak acid equilibrium, not a weak base equilibrium. And I plug in my equilibrium values to my expression. I'm going to highlight the two negligible x's in this problem. And what we will find is that they are indeed negligible. So what I'll be doing is cross multiplying the 1 and dividing by 1.5 to solve for x, which is equivalent to the H plus concentration of 4.8 times 10 to the negative 4. And as we know, we can solve for the pH by taking the negative log of the concentration of H plus in order to get pH from our magical box of pH power. The pH ends up being 3.32. Does this make sense? Well, for a weak acid solution, especially with the addition of a common ion, a pH less than 7 is appropriate. So another question. The pH of a 1 molar HF is originally 1.57, which is lower than 3.32. What did the addition of the salt do to the pH and why? Well, if we're answering it, the pH went up, right? It went from 1.5 up to 3.32. Does this make sense? Well, the pH is going to go up because remember, there was a shift in equilibrium which reduced the number of H plus ions. And if we reduce the H plus ions, we actually increase pH because remember, pH is the power or the potential of hydrogen in solution. And that is all for 15.1. See the next video for 15.2 on buffered solutions.